Alright guys, let's do this. I hope you're able to see the screen at least a little bit here. So I'm going to work with first today some of the problems from 12.3 in your packet, the limiting reactants. I know some of us were struggling a little bit with numbers 13 and on, so I will work 13, and then I will also do 19 here for you in a video. If you guys continue to struggle, I will probably also post 22 and 25 later on today. But let's at least get through these two here. So, as always, we're going to start with our balanced chemical equation. So for number 13, this is the chemical equation that was given to us. Anytime you're given a chemical equation, you need to double check that it's balanced. When we look here, we see that there's 2 and 4 oxygen, and 2 times 2 is 4 oxygen, 2 nitrogen, so this is a balanced chemical equation. Now let's move forward. So number 13, what they tell us is that we have 1 mole of O2 and 4 moles of NO. So like we were doing on Friday, our very first step will be to write that as a ratio, because we're going to figure out what that ratio will tell us. So if we've got 1 mole of O2 and we've got 4 moles of NO, that actually is also already a pretty easy conversion, but what we should actually do is put the 4 moles on top. So we're going to say it's actually 4 moles of NO per 1 mole of O2. Anytime that we're actually doing the division like we did in some of the prior problems, this is what we're trying to get to. We're trying to get one of the products to a 1 mole ratio. That way we can say if there's 1 mole, if we have this much of this O2, how much NO is there. So this is our given ratio. Now if we look back to this equation, the balanced chemical equation of what we actually have, our actual ratio is going to be, so we're going to look at how much NO, how many moles of NO are there. So here's the NO. Remember, our moles are given to us by the coefficient. So the coefficient for the NO in our balanced chemical equation is 2 moles of NO per, wow, look at that, there's 1 mole of O2. So this one is actually very, very easy. It should help you be able to better understand the concept, because when it comes down to this one being a not very easy to look at problem, it's kind of hard. If this were a fraction or portion of a whole number, it's a little harder to visualize. But here we're very easily able to see that for every 1 mole of O2, we need 2 moles of NO. So if you go to this given, we actually have in this problem 4 moles of NO for every 1 mole of O2. So that's very simple to look at and say, wow, okay, our O2 is going to be our limiting reagent because there's only 1 in each of these, so we can't say that there's more. This is what's going to stop us, because we could actually go up to 4, right, of NO, but because we only have the 1 mole of oxygen, we can't go any higher. So what is going to be our limiting reactant in this problem is the oxygen, because it's the one that we can't go any bigger on, because our given is only 1 mole. So we're going to say then that the limiting reactant in this number 13 is the O2, and the amount of NO2 that we have, we're then going to be able to calculate, because in this, we're actually only going to come to this portion. We're only going to actually have what we actually have. So we're only going to use the amount that is given in the balanced chemical equation, because we only have 1 mole of O2. So So how many moles of NO2 are in a given? There's only 2 moles of NO2 in the chemical equation. So for number 13, the amount of NO2 is 2 moles. The limiting reactant is O2, and the amount of excess we're able to determine because here we have 2 in what we actually have in our chemical reaction. But because we only have 1 mole of O2 and 1 mole of O2, we can still only use 2 of the NO. Therefore, you take the 4 moles from the NO, come up here, and you subtract the 2 moles of NO from the chemical equation, or what we're actually going to be doing. You get 2 moles of NO are what the excess are. So, for number 13, the excess are 2 moles of NO. Alright, let's move down to numbers 19, 20, and 21. This one's also a really good example. It's actually a really good example of using molar mass conversions to go, because these ones come out really easy. So again, we're going to have the same chemical equation, and it is still balanced. So O2 plus 2NO gives 2NO2. Alright, and again, this is 19 we're looking at. So what is given is the amount of O2 and the amount of NO. But because it's given to us in mass this time, we actually have to do one step before we can do that conversion. So what's given to us is 32.00 grams of O2. So guys, now I want you to think, how do we get mass to moles? This is what we did last chapter. We start with mass. We want to get to moles, because we want it to look like that problem in number 13 where we have a mole, so we can do molar conversion, because that is what we know with our balanced chemical equations, how many moles we have of each. So we're going to need something that has a mass in it and has the moles. What is one conversion factor that you know will have the mass of O2 and the moles of O2? We know from a periodic table what 1 mole of O2 is, right? So if we want the mass to cross off and we want to end up with moles, we know that the mass is going to go on the bottom. So it's mass of O2. And we're going to have moles on top. So mole of O2. We know what 1 mole of O2 is, because we know what 1 mole of oxygen is by looking at a periodic table. And 1 mole of oxygen is 16 grams. Because we have 2 parts of oxygen, we're going to take 16 times 2, which gives us 32.00 grams of O2, which will give us how many moles of O2 we have, which oddly enough, actually this entire thing crosses off, and we get 1 mole of O2. Now for the NO, we're going to do the same thing, because we want to know how many moles of NO we have. And we are given, here they tell us we have 60.02 grams of NO. So we go 60.02 grams of NO. And again, we think, what conversion factor is going to get us 2 moles of NO? We're going to need one that has mass, and we're going to need one that has moles. Therefore, we know the mass of 1 mole of NO. We want the mass of NO on the bottom, so that crosses off, and moles of NO on top. And we're able to easily figure out what 1 mole of NO is. Again, by looking at the periodic table. So, first of all, we look at nitrogen, which is 14.01 grams. So 14.01 grams. And we remember oxygen from before is 16.00 grams from the periodic table. So what we're going to do is simply take 16 plus 14.01, and we then get 30 30.01 grams of NO. Alright, so that tells us that 1 mole of NO equals 30.01 grams. So mass of NO crosses off, but this time we're going to take 60.02 grams divided by 30.01. So remember, when we multiply by a fraction, any number by itself is technically over 1. So you'll multiply across the top, multiply across the bottom, and divide the top result by the bottom result. Which is essentially, since this is times 1, this is times 1, you're going to essentially have 60.02 divided by 30.01, which gives us 2 moles of NO as a result. And again, we have an easy molar conversion, or molar ratio here, right? We've got 2 moles of NO for every 1 mole of O2 from here and here. So now we are right back to where we were on problem 13, right? Remember on problem 13 we had 1 mole, we got the big one on bottom, so we could sit every 4 moles of NO we had 1 mole of O2. Now this is the step we do, we figure out the actual is the balanced chemical equation. So the actual is going to be, so NO, we've got 2 moles of NO, and you can tell that by the coefficient on the NO. And if there is no coefficient, we know that is 1 mole of O2. Well, it looks like what we've been given is equal to our actual. So what that tells us is that from 19 for 20 and 21 there will be no limiting reactant because we're able to use them all up, and there will be no excess because we can use it all up. But we can still calculate the number of O and O2. So amount of NO2 is equal to exactly as the balanced chemical equation tells us. So we take 2 times N, and oxygen times, and 4 times oxygen, because we have 4 oxygen, take 2 times 2. Remember that these subscripts only apply to the one that's on, unless they're parentheses in. And this 2 applies to both of them. So I'm going to take 2 times 2 for the oxygen, and we have 2 nitrogen. So down here we're going to say 4 times 16.00 grams, and 2 times 14.02 grams. And then we add that up, and we get 46.01 grams of NO. Well, no, that's not times 2. So what we actually get is -2.01 grams of NO2. So this is the actual answer. Number 19, 92.02 grams, because it's just as the balanced chemical equation gives us. Respond to your bell ringer if you would like more questions videoed or more problems of any particular area.